Right. Well, with that, I will pass you over to Marcus, who I'm looking forward to the talk. Thank you.
Yep. I think I've got a microphone, which I think is it working? Yep. Great. Great. Well, I'm obviously very honoured to be here for your 70th anniversary. Very good of you to invite me. Are we going?
I think we're going.
We're going. Okay. Right. I thought I'd start by telling you something hopefully mad about black holes. And that is, if I were a black hole and I were to turn around like this, there would be nothing any of you could do to stop yourself swirling around with me. It wouldn't matter if you had the most powerful rocket imaginable. It wouldn't matter if you had access to all the energy in the universe. You wouldn't be able to prevent yourself from swirling around. A black hole spins at the heart of an irresistible tornado of space-time. Now, a black hole is a region of space where gravity is so strong that nothing, not even light, can escape, which is, of course, why they're black. Oh, sorry. Okay. The term, they most commonly form when a massive star gets to the end of its life, runs out of fuel, no longer able to generate the heat to push outwards against gravity. Gravity crushes the star down to a point, to a singularity. And the term black hole was only coined or popularized in 1967 by John Wheeler, who was an American physicist. He was the supervisor of another famous physicist you may have heard of, Richard Feynman. And before he coined the term black hole, there was very little research on black holes. And afterwards, the field kind of mushroomed.
You want to this?
And it just goes to show how important in science it is to coin a term that paints a vivid picture in people's minds. And so vivid a picture does it paint that there's probably nobody on the planet who doesn't know the term black hole. And we commonly use it in everyday language to say, I've lost my passport, I've lost my pen down a black hole. But in many ways, the term black hole paints entirely the wrong image, because the black holes that we see out in the universe are among some of the most phenomenally bright objects in the entire universe. So far from being black, they're extremely bright. And although we can just about see in some of them evidence of material falling in, the most striking feature of these black holes is of material coming out, often along titanic jets which stab outwards from the poles of these black holes across millions or even tens of millions of light years.
Yeah, I know, right?
Now, the
results back.
Yeah.
just over 100 years ago,
60.
black holes were considered to be so ridiculous as to not even be the preserve of science fiction.
Not bad.
But over the last century, just over a century, they've moved more and more into the center of science. Until now, we realize that black holes play some key, but still mysterious role in creating the universe we see around us. And in fact, all of you coming here to listen to me tonight, and I'll explain that a bit later. So my book is really about how they came in from the cold. And the story begins...
Is it a good mark?
I can...
Yeah.
How do I do this?
That's the letter.
Do I go backwards?
Okay.
Maybe a great.
It's very, it's very sensitive. It begins with this man, Karl Schwarzschild. He was the director of the Berlin Observatory
A bit more working
in
again.
August 1914 at the outbreak of the First World War. He immediately joined the German army. He didn't need to because he was 40 years old, but he was Jewish, and anti-Semitism was on the rise in Germany. He wanted to show he was a patriotic German.
Because you didn't show your
And he ran a weather station in Belgium. Then he calculated shell trajectories in France. And at the end of 1915, he ended up at a place called Mulhouse, which is on the Alsace front, the only part of the Western Front that was mountainous. And in November 1915, he went on leave to see his family, his children in Berlin, which was about 800 kilometers north on the train. And on the 18th of November 1915, he attended a lecture by this man. This is Albert Einstein in his rock and roll years. And Einstein had presented his revolutionary theory, or he presented his revolutionary new theory of gravity in a series of 4 lectures given 1 a week at the Prussian Academy of Sciences in November 1915. Now, Newton had imagined that gravity was like an invisible tether that connected the Earth to the sun and kept the Earth trapped in orbit forever. But Einstein had realized this is incorrect, and what a mass like the sun does is it warps the space-time around it, it creates a valley in the space-time around it. That's in fact what gravity is, it's the curvature of space-time. We can't actually see it, which is why it took the genius of Einstein to recognize what gravity is. And so, I can show you. So basically, the Earth goes around the upper reaches of this valley of space-time around the sun, rather like a roulette ball in a roulette wheel. So Schwarzschild went back to the Western Front, and in his spare time, he was completely captivated by this theory that he'd learnt about on the 18th of November. And he did something that Einstein believed was impossible. So what you need to know is that Newton had a single formula to describe gravity, but Einstein had replaced it with 10. So actually finding the curvature of space around any particular object, any physical object, was considered by Einstein to be impossible. But within a few weeks, on the Western Front, Schwarzschild did the impossible, and he found the shape of the space-time around a spherical mass, like a star. And he sent his result, this is what we call an exact solution to Einstein's equations. He sent it to Einstein in Berlin. Einstein was completely amazed to get a letter from the Western Front. He was also amazed to see that something he thought was impossible had been done. So he later presented this result at the Prussian Academy of Sciences. But Schwarzschild had not finished. He realized that if the mass became more concentrated, the valley of space-time would get steeper and steeper until eventually it would become a bottomless pit from which nothing, not even light, could escape. It would be cut off from the universe. It will be what we call today a black hole. Einstein never believed in black holes. He presented this result at the Prussian Academy of Sciences. He never believed in black holes. And the reason for that was if a body were to shrink down to a point, it would become infinitely dense, what we call a singularity. When you get a singularity in a physical theory, it's telling you your theory has been stretched beyond the point where it has anything reasonable to say. So the theory is broken. Now, Einstein had just spent the last 10 years, blood and sweat, trying to get this new theory of gravity, and he didn't want to hear within a few weeks that there was a flaw in it, so he never believed in it. Poor old Schwarzschild, at the time that he wrote to Einstein in December 1915, he developed blisters in his mouth. Quickly, they spread all over his body, weeping, bleeding blisters. He ended up in a field hospital. It was a while before his condition was diagnosed. He had a condition called pemphigus vulgaris, which is a condition in which the immune system attacks the skin. There's no cure for this even today, although it can be controlled with steroids. But of course, your skin, you control your body's temperature by losing heat through your skin. And of course, your skin is a barrier against pathogens, against disease-causing organisms. So Schwarzschild knew he was going to die, and he went back, he was taken back to Berlin, and he died in May 1916. But his idea did not die with him. So now I'm going to leap ahead about 50 years. Oh, that's Schwarzschild in his. This is the Royal Observatory, which was at the time was at Hurst-Monceau. This is about 1971. The Royal Observatory, Royal Greenwich Observatory, was in this moated 15th century castle not very far from Hastings. And in 1970, this man had come back from America. He'd been doing a PhD in New York. His name was Paul Murdin. And he had a wife and 2 young boys under the age of 5. And he badly, badly needed a permanent job. And the job that they gave him at the Greenwich Observatory was temporary. So he needed to make his name. And when he was back in New York, him and the other graduate students would sit around drinking coffee, and they would think, how do we make a discovery in astronomy? So the problem you have in astronomy is that there are more stars in the universe than there are sand grains around the edges of all the continents on Earth. How do you find an interesting sand grain? How do you find an interesting star? It's a similar kind of thing. Well, talking with all the graduate students, Murdin had come to the conclusion that if it emitted X-rays, it would be interesting, because X-rays are emitted by matter at millions of degrees. So that's going to be very interesting. In the early 1960s, the first X-ray telescopes were launched on sounding rockets. These were rockets that just went straight up in the air, spent maybe a minute above the atmosphere and fell back down again. And in that time, they discovered a handful of mysterious X-ray sources. But these telescopes were incredibly crude, and they weren't able to locate where these X-rays were coming from. So they were given the name of the constellations where they were found. And one of them was called Cygnus X-1. It was in the constellation of Cygnus. Well, in 1970, this was launched. This was NASA's Uhura satellite. It was an X-ray satellite. And sitting above the Earth's atmosphere, which fortunately for us, absorbs X-rays, it was able to look at the X-ray sky, and it found hundreds of mysterious X-ray sources. And Murdin got hold of the catalogue, and he looked at the box showing the possible location of Cygnus X-1, and he realized that it had shrunk. So he looked on star maps, and there was one interesting object in the field of view. It was a blue supergiant star, really powerful star, maybe 30 to 50 times the mass of the sun, pumping out 100,000 times more light than the sun. This was a very, very unusual star. But Murdin knew it could not be the source of the X-rays, because even a blue supergiant has a surface temperature of no more than 50,000 degrees. And it really needed to be millions of degrees to produce X-rays. So Murdin wondered, did it have a companion? Because if it had a companion, then material could probably be sucked off the blue supergiant star, spiral down like water down a plug hole onto the companion. And in that disk, which we call an accretion disk, the friction could heat it to millions of degrees. So did it have a companion? As luck would have it, Murdin was sharing an office. It was actually an octagonal turret room in the castle, and through the window you could see the moat and the geese grazing, on the fields beyond. It was quite an idyllic office. He was sharing an office with this woman. Her name was Louise Webster. She was an Australian. She was about the same age as Murdin. She was about 30. She'd worked in America too, and she was working with the director of the observatory, Richard Woolley, on a project to measure the speeds of stars in our galaxy. You're probably aware that if police siren comes towards you, it's a higher pitch, higher frequency. If it goes away from you, it's a lower pitch, lower frequency. And obviously it's an analogous effect with light. And high frequency light of a star coming towards you is blue shifted to the blue end of the spectrum, and red shifted if it's going away. So if this blue supergiant had a companion, then periodically, as it went round this companion, it would be coming towards us and going away. So was there a periodic blue and red shift in the light of this star? Well, Louise Webster was using the Isaac Newton telescope at Hertzsprung, which was a 2.5 meter mirror. It was a telescope built in the absolute worst place to build a telescope. It was in East Sussex, where it was always misty and cloudy. And this telescope would be deconstructed, taken on a ship to the Canary Islands, and reassembled at a greater cost than it actually cost to build it in the first place. Anyway, she very quickly found that the blue supergiant star was orbiting something every 5.2 days. So this enormously massive star was being whirled around every 5.2 days by an invisible companion. So Murdin and Webster sat down in her office and tried to calculate, using Newton's law of gravity, what the mass of the missing object was, the companion. And very quickly, they realized that it had to be more than 4 times the mass of the sun. and maybe even more than 6 times the mass of the sun. Today we know it's 15 times the mass of the sun. But there was nothing on photographic plates. And they looked at each other and they knew there was only one object that could be that massive and that invisible, and that was a black hole. So they found the first black hole in Cygnus X-1. So Murdin got his full-time job. He got a bigger house, so he was the first person in history to have his mortgage paid by a black hole. And he celebrated in a beachfront cafe in Hastings by buying his little boy's Knickerbocker glories. And I just mention that because what a contrast. The man who predicts the existence of black holes dies of a horrifying skin disease in World War I, and the man who finds or co-discovers them celebrates with Knickerbocker glories. Now, Louise Webster went back to Australia eventually. She had liver disease. She had one of the first successful liver transplants in Australia, but she got liver cancer and she died in Sydney at the age of 49. And she's been completely written out of the history of science. So if there's one thing that you remember from my talk today, please remember the name of the co-discoverer of black holes, Louise Webster. Now, the definitive evidence of the existence, by the way, they just inferred the existence of this black hole. They hadn't actually, it wasn't a direct measurement, it was an indirect measurement. The definitive evidence came on the 14th of September 2015. This is Livingston in Louisiana, where there's a 4-kilometer ruler made of laser light, and 3,000 kilometers away in Hanford, Washington State in America, is another 4-kilometer ruler made of laser light. And on the 14th of September 2015, a shudder went through through the Hanford ruler, and less than 100th of a second later, an identical shudder went through the Livingston ruler. And here you can see the traces. So the top panel shows you the signal at Hanford in Washington State. So from left to right, you're seeing about 100th of a second. And then the up and down motion is the stretching and squeezing of that 4-kilometer ruler. And in the middle panel, you're seeing Livingston. And in the bottom, you can see the two overlaid, and you can see they're pretty identical. This is the unmistakable signature of gravitational waves, ripples in the fabric of space-time, that were predicted by Einstein from his theory in 1916. Roughly 100 years earlier. They are the gravitational waves, the signature that you would get from two black holes merging. So this is the definitive evidence that black holes really do exist. So I want to tell you just something quickly about this event. Yeah, it happened about 1 billion years ago. So at a time when the most complex organism on Earth was a bacterium, 2 monster black holes were locked in a kind of death spiral, and they whirled around each other one last time. They kissed and they coalesced, and in that moment, they launched a tsunami of tortured space-time, which spread out at the speed of light. And it spread out really over a greater and greater volume over the last 1 billion years, until it finally, being diluted all the time, until it finally arrived on Earth on the 14th of September 2015, when it was very tiny. So the difference in the length that was measured of those 4-kilometer rulers was about 10,000th the diameter of a proton. So you can understand why 3 Nobel Prizes were given for the discovery of gravitational waves, because it was pretty incredible. But I just want to tell you something about this event. So in the explosion of a hydrogen bomb, something like 1 kilogram of mass energy is converted into other forms, ultimately the heat of the fireball. But in the merger of these two black holes, they were both about 30 times the mass of the sun, much bigger than we ever expected to see. Something like 3 times the mass of the sun vanished in a split second and reappeared as gravitational waves. So briefly, this object, this merger, the power in the gravitational waves was 50 times greater than the power emitted by all the stars in the universe combined. So to put it another way, had this merger emitted visible light rather than gravitational waves, it would have shone 50 times brighter than the entire universe. The most violent event ever witnessed by human beings. But in fact, we've actually seen brighter ones since. We've seen a merger that was 150 times brighter than the entire universe. But actually, black holes were discovered 8 years before they were discovered. But nobody realized. They were discovered really by this man, Martin Schmidt. He was a Dutch-American astronomer. I used to see him when I was at Caltech, but I never took lectures from him. And the story goes back to the Second World War. So in the Second World War, radar was developed. This was a means of transmitting invisible to the naked eye electromagnetic waves, radio waves, and picking up their reflection from objects like aeroplanes. And we all know that radar played a key role in the defeat of the Luftwaffe in the Second World War. After the Second World War, some of those radar engineers decided to be astronomers. And this was a really ridiculously daft thing to do because there was literally no evidence whatsoever that stars would produce appreciable radio waves. There was no evidence at all. So it was a really risky thing to do. However, during the 1950s, John Bolton, who was from Sheffield but had gone to Australia, he discovered extragalactic radio sources. So he found that there were mysterious sources of radio waves in the sky. The problem was that radio waves have a wavelength at least 1 million times greater than visible light. That means that a radio telescope creates an image 1 million times blurrier than an optical telescope of the same size. So it was not possible, just like with the X-rays, it wasn't possible to know exactly where these radio waves were coming from. And we needed to kind of identify them with a star or a galaxy. We couldn't do that. We only knew which constellation they came from. But an opportunity came to locate one of these radio sources at the end of 1962. So one of these objects was called 3C273 because it was in the 3rd Cambridge catalogue of radio sources, and it was going to be occulted by the moon several times. If there's one thing we know about the moon, it's its precise location. So if we were able to observe when 3C273 vanished and when it reappeared, we'd be able to locate where 3C273 was. And this observation was done by this Parkes radio dish in New South Wales. John Bolton, who people have forgotten who he is, but he was, as I say, he was from Sheffield. He'd actually founded this observatory and also the radio observatory at Caltech in California, where Martin Schmidt was. He's the only person to have founded major observatories in both hemispheres. Anyway, they observed this and they found the location. And the location, John Bolton sent the location to Schmidt at Caltech. And he looked on stellar photographic plates, and there was just a star. That's all there was, a star. It was actually quite a bright star. It was almost visible to the naked eye, but it was just a star. Later, it was discovered that it had a strange jet coming out of it, so it was an odd object. Anyway, just after Christmas 1962, Schmidt went off to Mount Palomar, which was, at the time was the biggest optical telescope in the world, a 5-meter collecting mirror in the mountains just north of San Diego. And his aim was to take the spectrum of 3C273. Now, the spectrum is obviously the light fanned out into its constituent rainbow colors. And in the 100 or so, 200 years ago, someone had first discovered that there were missing colors. And nature has been unbelievably kind to us because it's given every single one of its elements a distinctive pattern of these lines, rather like a supermarket barcode. So there's a barcode for every single element. So we can know what an astronomical object is made of. So Schmidt hoped we would find out what 3C273 was made of, and that would at least give us some hint what it was. So he took the spectrum, and would you believe it, there wasn't a single spectral line that matched any known spectral line. He was completely baffled. He took the spectrum back to Caltech. He showed it to all of his colleagues. No one could identify any of the lines. This was just after Christmas 1962. It lay on his desk until March
You wanted to
1963,
see.
when he got a letter from John Bolton in Australia, and Bolton said, we're going to submit a paper to the international journal Nature about the location of 3C273. Could you write an accompanying paper? Well, Schmidt panicked because there was literally nothing he could say about this object. It was completely mysterious. He came back from lunch one day at the Athenaeum, which is the Caltech club, and he started looking at the spectrum under a microscope, and he noticed that there was a pattern. There seemed to be a pattern. The lines seemed to get closer together as you went to the blue end of the spectrum, and they seemed to get slightly fainter. So there was a weird pattern. So he thought he would compare this pattern with a spectrum that he knew very well, which was what we call the Balmer spectrum of hydrogen. So hydrogen is the most common element in the universe. And you probably know that the electron, there's a number of energy states or orbits it can have. It can have an inner one, a second level, a third level,
Okay.
a fourth level, fifth level. And the Balmer lines are created when an electron moves to the second level. So from the third to the second, fourth to the second, fifth to the second. So when the electron moves to the first level, they're called Lyman lines, and they're in the ultraviolet. But all astronomers knew these Balmer lines of hydrogen. So he started comparing these Balmer lines of hydrogen with the spectrum of 3C273, and he discovered that they were Balmer lines. He'd never expected. Each one was shifted by 16% to the red end of the spectrum. He was looking at hydrogen. And this was really shocking, because this object was moving away at 16% of the speed of light. But no one had ever observed the star even moving at 1% the speed of light. And we'd seen things moving faster, but they were galaxies. So in 1929, the American astronomer Edwin Hubble, using the Mount Wilson telescope, which is just above Caltech in Pasadena, on Mount Wilson, had discovered that the universe is expanding. That its constituent galaxies, of which we now know there are about 2 trillion, are flying apart like pieces of cosmic shrapnel in the aftermath of a Titanic explosion, which we now call the Big Bang. And the further away a galaxy, the faster it was moving. So Schmidt was able to work out that to be moving at 16% of the speed of light away from us, this galaxy was 1,000 times further away than Andromeda, the nearest big galaxy. But it was really bright. And when he did the calculations, how could it be that bright when it was that far away? He realized it was pumping out about 100 times the light of a typical galaxy. And already, radio astronomers had found that this object fluctuated in brightness on very short timescales, something like a day or less than a day. And that tells astronomers that the object is less than a light day across. So this object was roughly the size of the solar system, but pumping out 100 times the light of a complete galaxy. But within a year, theorists realized there was only one possible source of this prodigious energy. It was matter swirling down through an accretion disk and heating up to millions of degrees onto a black hole. But not a black hole of stellar mass, not a stellar mass black hole, a black hole of millions or even billions of times the mass of the sun, a supermassive black hole. Now, at this point, I should tell you that quasars are known as active galaxies. So an active galaxy is a galaxy whose principal light doesn't come from stars. It comes from basically an accretion disk around a black hole. And quasars are just one of a zoo of these active galaxies. But together, active galaxies only count for 1% of all galaxies. So at this time, people could still think, well, maybe they're an anomaly. We don't have to worry about them. They're only, these objects, they're only 1% of galaxies. We don't have to worry about them. But everything changed with this. So this is the Hubble Space Telescope. As you remember, you probably all know, in 1990, it was launched with the telescopic equivalent of a squint. And it cost $800 million, probably billions in today's money, to fix it. It was the most complex mission ever undertaken by astronauts. And effectively, they had to put correcting spectacles in front of all of its instruments. But as you know, when we look at the stars from the ground, we're looking up through the turbulence of the atmosphere. And it's rather like lying on the bottom of a swimming pool, looking up at the lights on the ceiling. They flit around and get blurred out. But Hubble, above the blurring effect of the atmosphere, had super sharp eyesight. And in the center of scores of nearby galaxies, it was able to see that the stars were orbiting far too fast. They were like children on a speeded up roundabout. They ought to just be flung off. And the only way they were not being flung off is if they were in the grip of the powerful gravity of a very massive object. So Hubble discovered that there wasn't a supermassive black hole in only 1% of galaxies. There was a supermassive black hole in the center of effectively 100% of galaxies. And the reason that only 1% are active is because in only 1% are being fed. So in the 99% of cases, they've eaten all the stars and ripped apart gas, and they're starving. That's why they're dormant. But still, they still might not be that important because supermassive black holes are unbelievably tiny. So if you imagine a bacterium compared to a major city like, say, London, this is not London, but anyway, it's a pretty city. Imagine a bacterium compared to a city like London. The supermassive black hole is, compared to its parent galaxy, is like that bacterium compared to London. So would we expect a bacterium to control and orchestrate the street plan of London? We wouldn't. But the supermassive black holes do control their galaxies. And this was discovered from about 2000 onwards, and it was completely baffling. Because to give you an example, in every galaxy that we see in the local universe, the supermassive black hole is about 1,000th the mass of the central bulge of stars, the central sphere of stars. So there's obviously an intimate connection between the supermassive black hole and the stars. But that appears to be impossible because the supermassive black hole is very, very tiny, and its gravitational reach is only at most 10 or 20 light years, which is only about 1,000th the size of the galactic bulge. And yet they seem to have left their imprint. But what you need to know is that as far as supermassive black holes are concerned, size does not matter. It's the energy that's important. So if I were to walk past a house and a slate were to fall on my head, what would have happened was gravitational potential energy, that's energy that the slate had by virtue of its high location in a gravitational field, as it fell to a lower location, would be converted into other forms of energy. Energy of motion of the slate, energy of my headache. And we don't know how supermassive black holes form, but a very large amount of mass has to come together. And that's the equivalent of countless quadrillion slates all falling together. And when you do the calculation, you find that the energy involved in the birth of a supermassive black hole is 1,000 times more than the energy necessary to blow a galaxy apart. So in other words, to blow all of its stars to infinity. So there's more than enough energy there available for this supermassive black hole to impress itself on the galaxy. Only 0.1% of that energy needs to heat up, or we don't know how to heat up the gas around. Remember the gas around it forms stars. So there is a means by which it can, the energy is available for it to impress itself on the surrounding stars. What we see today is that the supermassive black holes project their power via these titanic jets which come out of the poles of spinning black holes. And in the 1950s, when radio astronomers first got enough resolution to see radio galaxies, or they're another type of active galaxy, in slightly more detail, they were able to see that there was two giant lobes, radio-emitting lobes, one on either side of the central galaxy. So it was obvious that there had to be some connection. between the central galaxy and the lobes. And that was only discovered in 1983. This is actually an image taken by the Very Large Array, which is an array of 27 radio dishes at Socorro in New Mexico in the desert. And it created this image. So you can actually see the central galaxy is the central point, and you can see the jet going from to the upper right-hand side. There is actually a counterjet going to the bottom left, but it's going into the screen, so it's actually redshifted. It's reduced in energy, so you can't see it so well. So imagine, what are you seeing? So imagine you had a high-pressure hose, and you fired it at a brick wall. That water would splash back, and this is exactly what you're seeing. So these jets have gone out from the central galaxy. They pushed the intergalactic medium in front of them, rather like a snowplow pushing the snow in front of it, until the snowplow finally gets stuck, and basically these jets have got stuck, and they've effectively turned the intergalactic medium into a brick wall, and you're seeing the material splash back. Now, we don't know how supermassive black holes form. We don't even know what came first, supermassive black holes or galaxies. Were supermassive black holes the seeds around which, because there's one in every galaxy, around which galaxies of stars formed? Or did galaxies of stars form first, and then maybe some dense cluster at the center collapsed to form a black hole? But we've got a strong hint about the answer to that in the last year, actually. So this is the James Webb Space Telescope, 6.5 meter infrared telescope, launched, I think it was Christmas 3 years ago, made of 16 hexagonal segments, basically because they couldn't fit it in a nose cone of a rocket, so it had to fold up. And it's at the Lagrange 2 point, which is, if you imagine the line joining the sun to the Earth, and you extrapolate another 1 million kilometers beyond the Earth, that's the Lagrange point. It's a point where we can leave something and it will stay there forever, pretty much forever. This at the bottom is a tennis court-sized sun shield. Well, last year these were discovered. I'm sure you've heard about them. They're called little red dots. Now, when they sent James Webb up, it looks back at the very early universe, when the universe is maybe a few percent of its current age, less than 5% of its current age. And the expectation was we would see lots of small galaxies. And the reason for that is we believe that the galaxies around today, including our Milky Way, have formed from constant collisions between smaller galaxies. In fact, from star streams in the Milky Way, we know that the Milky Way was formed from at least 5 collisions in its past. So we expected to see the building blocks of galaxies, the tiny building blocks. But in fact, what we've actually seen is galaxies which are much bigger and much more evolved than we expected, black holes which are much bigger than we expected, and the whole early universe has turned out to be totally baffling. And these objects are very baffling. They're called little red dots, and they are really, really tiny galaxies. They're between 1% and 0.1% the size of our Milky Way. So they're maybe 100 light years to 1,000 light years across, really, really tiny. And well, why are they red? Well, you'd think they're red because we're looking at the very early universe. So we're looking back when everything was compressed into a much smaller volume. So when we look back to a redshift of, say, 10, we're looking basically everything's about 10 times closer, something like that. And that means that the general gravity in the universe was much stronger. So the light has had to climb out of that gravitational well to get to us, exactly the same as the light climbing out of the gravitational well of the black hole. So it's lost energy and become reddened. But when you compensate for that, so you exclude that effect, you find these objects are still red. And what we see, the spectra of both stars and a supermassive black hole. So what we're seeing is the accretion disk, X-ray accretion disk of a supermassive black hole, but the black hole is shrouded in dust. So that energy is absorbed and re-radiated as infrared. So the important thing is when you do make these observations and you deduce how big the supermassive black holes are, you find that they're between 1 and 10% the size of the mass of stars. Remember today, they're only 0.1%. So this is a strong hint that the supermassive black holes came first, that they were the seeds. So in these early galaxies, they dominate and the stars are not as important as they are today. But as the universe evolved, more and more stars formed and the supermassive black hole kind of shrunk as a proportion of the mass of the galaxy. So that's a really strong hint, but we still don't know how they originated, but it looks like they were the seeds around which galaxies formed. What was I going to say? Yeah, well, if there's a supermassive black hole in every galaxy, that must mean there's a supermassive black hole in our galaxy. And there is. It's called Sagittarius A star. It was discovered exactly 51 years ago in 1974. And these two astronomers decided to try and measure its mass. So on the left is Andrea Ghez. She's an American astronomer, works in California. And on the right is Reinhold Genzel, who's in Bonn in Germany. And they realized that there was a very dense, tight cluster of stars around the central Sagittarius A star. It's called the S cluster for Sagittarius. And they realized if they could track the orbits of these S stars, then they could use Newton's law of gravity to infer the mass of the central black hole. The problem is, of course, looking up through the atmosphere, this cluster is completely blurred out. They've used a variety of techniques, but the most recent technique they've used is adaptive optics, which you're probably aware of. And this is where you have a mirror which can be flexed hundreds of times a second by hundreds of little tiny pistons behind a thin mirror. And you fire a laser beam up through the atmosphere and you pick up the reflection and you use a computer to work out how to flex that mirror to compensate for the turbulence in the atmosphere. So you effectively get a telescope in space, even though it's on the ground. And using this technique, they have followed over several decades now the orbits of several dozen of these S stars. And they swing in really close to this invisible object and when they're going really, really fast, and they swing back out again. Some of them, when they're in close, are going at something like 2% the speed of light, so faster than any stars we've ever seen. And this allows you to determine the mass of Sagittarius A star very accurately. And they determined that it has a mass of 4.2 million times the mass of the Sun. And for that, they got a Nobel Prize, which was, I think, about 3 years ago. And there was no mention of Louise Webster when they got that Nobel Prize, by the way. But 4.2 million solar masses, that's a real tiddler. This is a real mystery because it's thousands of times smaller than the supermassive black holes in the quasars. You know, they're up to tens of thousands of times, 10,000 billion, tens of thousands of millions. What am I talking about? They're tens of billions of times the mass of the Sun. So this is 1,000 times smaller. And even more, the supermassive black hole in Andromeda is the nearest galaxy, and it's very similar spiral galaxy to the Milky Way. Yet its supermassive black hole is 50 times bigger than ours. So it's a real mystery why we've got this tiddler of a supermassive black hole. But it's probably related to you all coming here tonight, because in the galaxies with the really big supermassive black holes, the jets are very powerful. So they push away, they drive away all the gas out of the center of the galaxies. So they snuff out star formation after one generation. But that's never happened in the Milky Way because the jets and the black hole are too small. And so in our galaxy, we've had multiple generations of stars. So as you know, the Sun is a third generation star. So 2 generations of stars have lived through their lives, exploded. The next generation is formed from the congealed out the debris of the previous generation. And in each generation, more heavy elements have been forged by those stars. So more carbon, more oxygen, more calcium, more iron, precisely the elements needed to make a rocky planet like the Earth, precisely the elements needed to make life like you. So it could be that we actually owe our very existence to a black hole, that we've got an unusually small black hole, which of course has got real implications for the rest of the universe and where we're going to find life. We don't know why we've got this tiny black hole, by the way. But yeah, so Gez and Genzel only inferred the size of the supermassive black hole, just like Webster and Murdin, it inferred the size of the black hole in Cygnus X-1. Hadn't actually seen it, but we've got our first image of a black hole. It was taken by the Event Horizon Telescope. This is an array of identical radio dishes with identical radio receivers spread over the planet. Initially, it had 8 dishes. There's one in Antarctica, there's one in Hawaii, they're all over the place. And what you do is you record, get them all to look at the same object at the same time, record the radio signals on hard disks, fly those hard disks to supercomputers. There's one at Haystack in Massachusetts in America and one at Bonn in Germany. And on those computers, you process this and you end up with an image as if you'd had a telescope the size of the Earth. So one of the things I should have told you is that, yes, radio dishes have create images which are 1 million times blurrier than optical dishes of the same size, but you can compensate for that by having a bigger radio dish that allows you to see more detail. But when you build a radio dish more than 100 meters across, it collapses under its own weight. So the only thing you can do is actually have an array of radio dishes. It's very much more complicated, but you can do it. And this is what they did here. I just want to emphasize what a crap telescope this is. Imagine you had an optical telescope, optical mirror, and you blacked out all of it except for 8 tiny little dots of silver. Imagine the terrible image you get. Well, that's what you get. But of course, that's all they can do. And with this quite crap telescope, they created these 2 images, which I'm sure you're aware of. And the first one is the black hole, the 6.5 billion solar mass black hole in the nearby galaxy M87. And on the right is Sagittarius A star. And the interesting thing about this is that they look the same size, because actually M87 is 1,500 times bigger, more massive than Sagittarius A star. But coincidentally, Sagittarius A star is 1,500 times closer. So they look exactly the same. And they look remarkably similar. So basically you're seeing super hot material. I mean, this is color coded. This isn't really what it looks like because obviously we don't have radio eyes, but you're seeing super hot material and the void in the middle is exactly what you'd expect. It's the black hole. In fact, it's what we call the shadow of the black hole, because light does not come to us in straight lines. It's bent by the black hole. So we're seeing what we call the shadow. So here is M87 again. You can see how big it is, how big the black hole is, the void in the center, because I mean, it's very, very big. And so when material goes into this void, it's rather like water going over a waterfall. This material, once it goes over the edge of that void, what we call the event horizon of the black hole, it is never seen in our universe again. And in the center of the black hole, or inside the horizon of the black hole, which is the what we call the point of no return for infalling matter, is called the event horizon. Inside, we believe that space and time are torn apart into something more fundamental. We've got no idea what it is because we don't have a quantum theory of gravity. We need a quantum theory of gravity to do that, but we think that space and time actually come to an end inside the black hole. So I just want to leave you with this one thought, and that is, as human beings, we tend to beat ourselves up for all the terrible things we've done to the planet, global warming, pollution, Donald Trump. And I think sometimes we just need to pat ourselves on the back, because we are a jumped up ape that came down onto an African plain a few million years ago. We've got a brain which is 1.5 kilograms of jelly and water, but we have seen to the edge of space and time. Thank you.
Right, thanks. That's excellent talk. Thank you. I was wondering on the little red dots, how do we know that's all there is that they're seeing there, and it is that kind of, it's not just a there's something much more fainter around it because it's so far away.
Yeah, we
that
don't.
That is the entire mass.
No, we don't, and that's a very good question because, I mean, initially, when we discovered quasars, people said, well, they're actually in the hearts of galaxies, but they were so bright that we couldn't see the stars around them. You know, it's like I don't know, trying to, yeah, I mean, the stars were just faint, they were outshone. So it is possible, yeah, that there's more galaxy there, yeah. I mean, this is a very recent discovery. They only announced it in the last year, but they're very, very exciting, you know. I mean, I saw something in New Scientist today about possibly we've observed the first primordial star, the first population 3 star. So because of there's no chance of us seeing these stars directly. They are the first generation of stars to have formed after the Big Bang. They would have formed from the pristine hydrogen and helium of the Big Bang. They wouldn't have had all the heavy elements in that present-day stars have. And the theoretical evidence is they would be very large, and they would have gone through their life histories and blown up in a few million years. They wouldn't be bright enough for us to see, but there's an alignment where this particular star has been magnified by the lens of an intervening galaxy. So yeah, I mean, it's all very new. I mean, your question is a really good question. It could be there's more to those galaxies. You're right.
Maybe yes. There you go. Thank you.
You talked about stuff coming out of black holes. It's not actually coming out of the black hole, is it?
No, it isn't. No, that's right. Nothing can come out of a black hole. That's almost a defining feature. But so we're actually seeing, yeah. So when the accretion disk is external to the black hole, and if you even Hawking radiation, which I should tell you that there are 2 types of black holes, right? So there are real black holes in the real universe, which are the black holes that you as an astronomical society are interested in, and then there are the theoretical mathematical objects of black holes. And most of the books are written about those, right? And you know, can you travel through time, fall in a black hole? You know, would you turn up in another universe if you went into one? All complete speculation. So my book is really about the real people who have discovered real black holes. So, but I mention this because Hawking radiation is a prediction, a theoretical prediction, and even Hawking radiation itself doesn't come from inside a black hole. It comes from just beyond the horizon. So nothing actually comes out of the black hole.
Maybe yes. Right. Well, hold on.
Right. I'm going to stand up again now. Yes.
Sorry, you mentioned dormant black holes.
Yes.
Can you characterize a dormant black hole and how that differs?
Well, a dormant black hole is just not being fed. So in 99%, I mean, in a Sagittarius A star is dormant at the moment. I mean, there is evidence that it has flared up in the past few million years, because we do see things, tantalizing things like shells of gas coming out. So it could have switched on, but in most galaxies, they've just eaten up everything up and starved to death. You know, that's what's happened. And of course, there are no quasars in today's universe. Okay, so I mean that's probably the fundamental observation that disproved the Fred Hoyle's steady state theory, because the theory said that the universe would be the same at all times, but they existed in the past. And the reason they existed in the past is because conditions were different in the past. Everything was closer together, you know. So there was a spate of star formation about 10 billion years ago, which was about the same time that the quasars were prevalent as well. So they were basically being fed more at that time, and then since then, there's not enough for them to eat, unfortunately. Well, fortunately for us.
Thank you. Oh, hold on.
How common are Tiddler black holes like
Tiddler
ours?
black holes. Well, you see, we don't know. I said there's something extremely unusual about our supermassive black hole. It's very tiny, but it could be that they're very common, but we just haven't been able to see them at great distances in the universe. I mean, we can see the ones that are sucking in a lot of material and are, you know, pumping out a lot of energy, but it could be that they are very common. And I say we don't know why we've got a small supermassive black hole, but it's possible that we didn't have a small one at some time in the past, because when galaxies collide, they generally have a supermassive black hole at the center, and generally those supermassive black holes merge. But if their spins if they're spinning are misaligned, one could be ejected. So it's possible that we had a bigger supermassive black hole, but it was ejected into intergalactic space. And these things could be flying all around the universe, but we would not see them, because unless they're sucking in material, we can't see them. Just like the only stellar black holes we see on the whole are in binary systems. There may be loads that are on their own, but we've got no way of seeing them. They have to be sucking in material for us to see them.
Thanks.
Thank you. Any more?
Oh.
So you said that we think that all galaxies have black holes, but there are dwarf galaxies out there. Is there some cutoff below which we think they don't have black holes?
Well, we don't know. We don't know. I think there are definitely supermassive black holes in some dwarf galaxies, but again, we don't know, because once you get down to small sizes, I mean, look, it seems bizarre that there seem to be two types of black holes in the universe. You know, that there are stellar mass black holes, and we're seeing with LIGO, the Gravitational Wave Observatory, one's up to, well, we're seeing forbidden black holes. We're seeing black holes which shouldn't exist, because the supernova that created them are what we call pair instability supernova, and they should have blown the star apart and not formed a black hole. So we're certainly seeing that the black holes we're seeing merging, we infer that the individual black holes resulted from earlier mergers, you know. So anyway, it's very unlikely that there's going to be two populations of black holes, you know, ones that are stellar mass and ones that are supermassive. So we're pretty certain they've got to be intermediate mass ones, you know, because the big ones must have grown from the small ones. And there is some evidence of intermediate mass supermassive black holes, thousands of times the mass of the sun, but they're more difficult to see at great distances, you know. Yeah, there's probably a whole spectrum of them, and they might even be smaller black holes, you know. And in fact, we all know that the visible matter is outweighed by a factor of 6 by dark matter, which we don't know what it is, but one possibility is that it's made of black holes, although they'd have to be quite small, and they haven't been ruled out. And when you hear of all the possibilities for what dark matter could be, they're intentionally speculative, you know, hypothetical subatomic particles, you know, from exotic theories. But the one candidate that is strong is black holes, because we know they exist.
So Marcus, do you think it's faintly possible that all the black holes once started as the whole universe inside one black hole?
Yeah,
I read an article about this recently, so it's not totally blue sky.
No, the universe is not inside a black hole. And the reason for that is that inside a black hole, we would definitely not expect things to be flying apart. And the universe is flying apart. So it's doing the opposite of what you'd expect if we're inside a black hole. So we don't have to worry about being in a black, we're not in a black hole.
Marcus, thank you very much. That's a fantastic talk. And you can tell from the questions, everybody was very excited and interested in your talk. So please thank Marcus again.
And if anyone would like a signed book, I bought books. I'm a sad author. You know, I bought all these books on the train. So please come up.
Whilst you're buying your books from Marcus, there is tea and coffee outside. Remember, it's £2 each. And we'll start again at in 20 minutes. So
Do you
at
think anyone would be interested?
20 minutes at 5 minutes to 9. So thank you very much.
If anyone would be interested, I thought so. You never know, do you? Right, thank you very much.